So one question that comes up usually after the excitement of the semester starts and you're settling down and you're getting used to the courses and the material that the courses have and what the courses expect of you is maybe worth a moment just to try to make clear what 6004 expects of you. So we actually have a bunch of material online. We obviously have the lectures and there's the recitations. I'm actually pretty flexible about what you go to and what you don't. I feel you're at the stage in life where you make your own choices about what's a good way for you to learn. But the key thing is that you should pick some way to learn. Other ways to learn involve, we have tutorial problems posted on the website. It says tutorial problems on the navigation bar. You can go there, and there's a set of tutorial problems for each lecture. And then there are a bunch of old quizzes posted there. And everything comes with answers. Now, we try to make it so that you have a chance to work on the questions before you see the answers, but the order in which you see answers and work on problems is sort of up to you. But I'm here to tell you that engineering, and particularly the engineering in 6004, is not a spectator sport, right? It's not something where you just watch it happen and then you'll just magically know. Most of the skills and concepts, you'll do much better if you actually roll up your sleeves and try to do them yourselves. So, the analogy is, I don't know if you've watched late night TV too much, but there's always these people demoing these fantastical products, and they make it look very easy. So I can make 004 problems look pretty easy. But when you go home and you try, you pay your $38.95 and it arrives, and you open up the box and your magic Ginzomatic or something comes out, and all of a sudden it's not so easy to use because basically there's a skill that you have to learn. And the same thing is true with unpacking and using the 6004 skills and concepts. You really do need to roll up your sleeves and try them. And so if you said, what should I be doing? What I would recommend doing is you go to a lecture and you go home or lecture and recitation, go home and you take the tutorial problems, and without looking at the answers, you try to do them. So the tutorial problems and the old quizzes are really meant to be self-assessments. Do I know what I'm doing? Am I done here? Am I good to go? Can I go, do something else? Or do I have some studying and learning to do? So I encourage you to actually, make a regular process of using those things as self-assessments, looking at the answers when you struggle a little bit, and then ask questions when you don't. We have lots of staffing in the lab. We have Piazza, and I can tell when somebody has, struggled with the material. They ask a Piazza question. You can sort of say, well, there's a person who tried it and didn't quite get it yet, and so there's a learning opportunity there, a teaching moment, and that's really, why we have staff, is to help you with those. So please roll up your sleeves and give it a try. Just watching it go by, you're not going to be nearly successful at engineering if you treat it as a spectator sport. Okay, sermon off, teaching. So today what we're going to do is to run off and sort of tackle the problem of, we actually now have a little set of CMOS logic gate building blocks we could use. They compute fairly simple functions, NAND and NOR and invert of a small number of inputs. Now what I want to do is address the problem of building much larger combinational circuits and talk about systematic ways of designing the circuit based on its functionality. So we actually have, we've been using up to now words to sort of describe the functionality inside a box. What we're going to do today is to look at more systematic techniques for describing the functionality of the box of a particular combinational circuit, and then how to go from those systematic descriptions to circuit implementations in a more or less straightforward, I can show you how to do this in a mechanical way sort of process. So the first description that's probably comes to mind and is actually, in a way, I find in some ways the most usable, is the notion of a truth table. If I have a box with a certain number of digital inputs, in this case 3, I can make a table that will allow me to exhaustively specify for each combination of digital inputs the expected digital output. So with 3 inputs, and each input's a digital input, so it can have one of 2 values. So we have 2 times 2 times 2, or 2 to the third possible input combinations, and you just list them. Here they are. They're done reasonably systematically here in terms of how I just enumerated all the possibilities. And then for each possibility, the output column, in the case of a single output, or if I had multiple outputs and I have multiple columns in my truth table, tells me exactly the functionality that I want. And the reason that I like truth tables is it makes me think about all the possibilities. Because I can sit down here and say, okay, in this particular case, what should I do? And because I have enumerated all the cases, I'm not going to miss one. Right? So truth tables help us be very systematic about describing the functionality we want. There's an equivalent representation, which is the Boolean equation. Right? So it's a little algebra involving binary values, 0 and 1 values. We use the variable names here to sort of be a stand-in for a particular input. And when you tell me that a equals 1, I can do Boolean arithmetic to figure out what the value of, in this case, y would be. So I tell you a, b, and c. It borrows standard mathematical notation, so we use plus for the Boolean operation or. We use times for the Boolean operation and, right? And in fact, the standard precedence rules apply. If you see things that involve both ands and ors, we expect you to do all the ands before you do any of the ors. Just like if you see a mathematical formula, you expect the multiplication to be higher precedence, to be done first before you do any of the addition. You can use parentheses to specify a particular order, of course. I will point out that we often use this little, either a multiplication sign or this little, in fancy typesetting, we use this little center dot to indicate multiplication. It gets tedious to write all those little dots. They're hard to read. So as in many mathematical formula, we often use implicit multiplication. If there's two literals next to each other, here B and A, if they're standing next to each other, we know is telling you that there's a multiplication in there. So sometimes we leave out the explicit and operator and just it's in there implicitly. Okay, and the little over bar here means negate. So C with an over bar stands for not C. Right? So that has the highest precedence, and then so this equation here is not C and not B and A. And then or with 4 other terms. So any questions about the basic notation behind our logic equations? Okay. So the first thing I want to do is to describe how to systematically go from a truth table to the corresponding logic equation. And you'll notice that the first step I'm going to do, one that will always be guaranteed to work, it produces a particular form of logic equation that we call sum of products. It's basically, there's a bunch of what we call product terms, so and operations that are clustered together. So here's a 3-element product term, another 3-element product term, so forth and so on. And then we sum them together. So it's sum of products is the same way of saying it's the OR of ands. Okay, now you notice there's 4 ones in the output column here, and what I'm going to do is develop a product term that where this Boolean equation is true exactly in the situation that corresponds to this particular 1 in the output column. So when C is 0 and B is 0 and A is 1, that's one of the circumstances in which we want Y to be 1. Right? So it's one of the products in the sum. So each one of these terms represents an opportunity for Y to be 1. So if this equation is true, this product term produces true, Y will be 1. Or if this one does, or if this one does, or if that one does. Of course, maybe more than one applies. Not in this particular case, but there's no reason why the product terms can't overlap. But they're describing all the combinations of inputs for which the output will be a 1. So C is 0. So not C. B is 0, not B. And A is 1, so A. So not C, not B, and A this equation is true exactly when the combination of inputs corresponds to this row of the truth table. And in fact, since there are 4 such rows, and there are going to be 4 such product terms. So if you look at this one, this is C is true, B is true, A is false. So C is true, B is true, and A is false, not A. Got it? Very, very straightforward. So if you can give me a truth table, I can give you a Boolean equation. If you give me a Boolean equation, I can plug in all possible combinations of the values for A, B, and C. okay, and build the truth table, line by line, simply by evaluating the equation. So we can go back and forth between those two things. Now, the reason that we like the logic equation is that it tells us exactly a circuit that can be built that will implement this function. What we're going to do is to use AND gates to do ANDs, and OR gates to do ORs, and inverters to do NOTs. And you can think of this as a textual recipe for the combination of ANDs and ORs that need to be put together to actually construct the circuit. So the building blocks, at least in this slide that we're going to use, the so-called sum of product building blocks, are the inverter. Here we see the symbol for the inverter, these little bubbles that you see in the schematic diagrams, in the schematic icons. Those are inversions. So they represent, something. So the triangle here is almost universally an amplifier or a buffer. It changes nothing. But with the bubble on the end is an inverter. It's something that takes in a signal, perhaps amplifies it, and then inverts it. In the case of a digital thing, it turns ones to zeros and zeros to ones. That's what the truth table is telling us. And then that becomes the output. We have AND gates and we have OR gates. You should get familiar with how these symbols look, and anybody who designs logic gets very good at reading these things. The AND gate has the straight back. The OR gate has the curved back here like this. You can see the OR is generally a more curvy object than the AND. Little practice and you'll get those. Keep in mind that in CMOS AND, we can't build AND directly. So this gate here, AND, is actually, if I looked inside of that, what I would see is a NAND gate, which hopefully yesterday in recitation you learned how to build with FETs, okay, followed by an inverter. So we're going to use this as our building block, but keep in mind that inside what we have is actually the actual CMOS gates that we can build using NFETs. And this is actually two CMOS gates in series. Same thing with OR. That's a NOR followed by an inverter. Okay, so sum of products is really pretty simple. We basically use inverters to form the inverted literals. We use the AND, here are 3 input AND gate to AND those 3 input terms together. And then we use a big OR gate to form, in this case, the 4 element sum. And so I can come up with a schematic representation for any Boolean equation that you give me. And of course, then I can I can start with the truth table, come up with an equation, and turn that directly into a sum of products implementation. So what's the propagation delay here? Well, it sort of looks like there's 3 levels. No matter how complicated the sum of products equation is, in the end, there's some inversions, some ANDs, and some ORs. Okay, this is slightly a bit of a delusion because obviously with super big logic equations, I would have to have ORs, a 72 input OR if I had 72 product terms here. And it's unlikely that I can actually buy a 72 input OR gate from anybody. So we're going to look into some of the nudgy little details about how to build what's called wide fan-in gates, gates with many inputs, out of actual building blocks that only have 2 or 3 inputs. So we'll talk a little bit about that. Okay, so this is very systematic. In some ways you could stop, go home. You would be able now to produce a circuit diagram for any combinational function that I happen to give you. Now, you might say to yourself, gosh, there are a lot of gates in this. And you might say, well, is there actually an equivalent expression which produces one and exactly the same combination of input values as this expression does, but involves fewer gates? So the notion of minimizing the logic, that's actually sort of the fun part of doing digital design. And that'll be what we'll talk about in the middle of the lecture. Okay, so how do we deal with suppose I only have 2 input gates. How do I make bigger gates? Well, I can use associativity to help me out here. Right? I want to do a 3-way, an AND of 3 things. I can basically AND 2 of them together and then take the output and AND it with the 3rd input. And that's really just saying that the AND operation is associative. A and B and C is always, is mathematically equivalent to A and B, the quantity A and B, ANDed with C. So associativity shows us how to build big, wide gates out of little gates. We just do the operations 2 terms at a time. 4 terms, sort of the same. I just use associativity this way. Actually, some of you may be looking at this and say, wait, there's another way I could do the AND of 4 things. I could AND A and B, and I could AND C and D, and I could then AND those 2 outputs together. So these are 2 equivalent circuits. Why might I choose one over the other? Which one should I choose? Is there just, one's always good? Yeah.
The bottom one has a lower propagation delay, and the top one has a lower contamination.
Okay, so there's some difference in the performance between these 2 things. If I think about what happens as the number of inputs gets bigger and bigger and bigger, the top one, the propagation delay increases linearly with the number of inputs. The bottom one, it increases logarithmically. Right, so you can say, in general, if I know nothing about the timing of the inputs, I'm likely to get Z faster with this tree-like structure than I am with a chain-like structure. But there is a circumstance, yes? Oh, I'm just saying that you could use OR gates. I mean, the method I'm showing you to actually build wide gates out of smaller gates, that applies to ORs as well as ANDs. OR is also associative. Sorry if that was confusing. So everything I've shown in this slide, you can take all the AND gates and draw in OR gates, and now you know how to do a 4-input OR gate. It would work equally as well. Can someone think of a situation in which maybe this circuit here, the chain circuit, might be more advantageous from a propagation delay point of view? Yes? Right, so there's this notion that this is sort of being computed incrementally, right? And that's a good answer, and we're getting a step in the right direction because that suggests there's a situation involving when the inputs are arriving that computing incrementally is actually to our advantage. Yeah.
If D is 0, it has a lower propagation delay.
So that's a value-dependent thing. If you knew D was 0 a lot, Z would be correct very quickly. But another observation is that if D arrives late in the game, so because of the pass of the circuit, not everything is going to be computed at exactly the same moment, different length pass. So that means that we may have some complicated computation that involves D. We still may want to compute Z, but in this case, the propagation delay from D to Z is only 1 gate. Here it's 2, right? And so if you know something about how long it takes, when exactly inputs are arriving, you might choose the top gate because computing incrementally, I can get the AND of A, B, and C done early, and then just do that final step when D arrives. So this sort of trade-off of thinking about the performance of your circuit and building a circuit that's fast, I mean, this is a factor of 2 difference, right? This is this factor of 2 propagated all the way through all of your thinking makes a difference between a 1 gigahertz processor and a 2 gigahertz processor, right? I mean, so factors of 2 are worth going after. So it's fun to think. So the challenge of doing good circuits is not just they compute the right answer, although that's certainly a basic requirement. Fast is no good if the answer is bad, if the answer is wrong. But assuming you're getting the right answer, figuring out exactly how to build the smallest, fastest circuit to produce it, that's sort of where human beings can lend their expertise. We're going to actually want to use, so the real building blocks that we have are NAND and NOR. So here's the schematic symbol. So for NAND, it's an AND gate with an inverting bubble on the output, or NOR gate has an OR body with an inverting bubble on the output. Those are our actual building blocks. It turns out that designing with inverting logic is something you have to practice. See? So I'll show you a technique, though, by which you can design positive logic, sum of products, and I'll then show you a systematic way of converting it into using NANDs and NORs, which is actually what we really want, because that way we're not building in a lot of little hidden inverters inside of our schematics. We're only doing inversions that we actually need to do. The final interesting building block is the XOR, exclusive OR. You'll meet it in lab 1 as we do arithmetic. This is critical for doing arithmetic, the XOR function. It's one of the basic gates that we use to do all sorts of computation. It's actually a big gate, right? So these guys here consist of 4 FETs each, 2 NFETs and 2 PFETs. This guy actually has probably 10 PFETs in it, 10 MOSFETs, 5 each of NFET and PFET, right? So this is actually a big gate, right? And so XORs are expensive, but they actually are the quickest way to do arithmetic, as we'll see in a couple lectures. Okay. So I want to say some things about NANDs and NORs, because they are the building block that the CMOS gods have given us, so it's important to understand them. First of all, they're universal. Okay, and what do I mean by universal? Well, we know from a sum of products form that we can implement any combinational logic function using inversions and an ANDs for the product terms and OR for the sum terms. And so what I'm going to show you here is here's how you could build an inverter using NAND gates, and here's how to build an AND gate using nothing but NAND gates. Not that I would suggest you actually do this, but this is sort of a conceptual proof that all I really need are NAND gates. And that's what I mean by them being universal. I can implement any combinational logic circuit can be implemented completely with NAND gates. And in fact, the same is true of NOR gates. So NANDs and NORs are universal gates. So if your stockroom says, I only got 1 bin, I'm only going to order 1 thing, if you tell them to order AND gates, you're going to be out of luck because there's things you can't build. But if you tell them to order NAND gates, then you can build anything. Same thing true with NOR gates. NAND and NOR are universal. So that's what we mean by universal. Okay. And that's good news because CMOS prefers us to use NAND and NOR. And in fact, to build an AND gate, we actually use a NAND gate followed by an inverter. This is just a NAND gate wired as an inverter. So, okay. So this is actually sort of an interesting slide for those of you who like to hack circuits. Here are 4 different circuits you could draw using our standard cell library. The standard cell library has in it a 4-input AND. It has a 4-input NAND and an inverter, and then of course it has some smaller gates. I'll talk more about this, particularly this NOR gate in a second. But all 3 of these circuits implement 4-input AND. Notice that they're getting faster. TPD is getting better, but as the TPD is getting better, they're getting bigger. Right? So I have a choice of sort of faster and bigger or smaller and slower. So you can say, which one of these I should draw? Well, that depends a little bit on whether you care about the speed. This is the fastest you can do you can do the AND of 4 inputs using our standard cell library. The point of the matter is that small fan-in inverting logic is the sweet spot for high speed. The logic tends to get big. This logic is 50% larger than that logic, but is also twice as fast. Okay, any questions? Let's talk about this. Why didn't I just put another NAND gate there? So what I wanted to compute, I'm trying to compute A and B and C and D, and what I've tried to do is to start, doing these 2 guys first. What we're noticing is that what I really compute is the NAND of A and B and the NAND of C and D. Okay, I can't use a NAND gate here. So the NAND operation is not associative. In other words, NAND of A, B, C is not equal to the NAND of AB NANDed with C. Those aren't equivalent. The NAND operator is not associative. So I can't simply build trees and chains of NAND gates to do big NANDs. I have to use a more complicated logic equation. In this case, what I've done is to use De Morgan's law. And what I've noticed, the particular one I'm using, is I put a NOR gate here. So the NOR of A, so this is A, B, and then invert the whole thing. So this is the logic equation for NOR. I've noticed that's equivalent to the AND of NOT. So the NOT of OR is the same thing as the AND of NOTs. That's what De Morgan's law is telling us. And what I've done is to I've taken my schematic here. And what I've really drawn is this schematic, where this is actually a NAND gate. It's just the demorganized version of the NAND gate. Instead of drawing an AND with an output, let's try this again. I'm busy misspeaking myself. Okay. What I've drawn is this. So this is actually a NOR gate. This is a NOR gate. Okay, I've just moved the bubble to this side and changed the body into an AND body. So these two are exactly the same. How do you prove that two logic functions are the same? You just build truth tables and say, look, they're the same truth table, so they must be the same. Okay, but by redrawing it this way, you can sort of see that this bubble and this bubble and this bubble and this bubble sort of cancel them out. An inverting output with an inverting input boils down to I'm just passing this. And now it looks like a tree of ANDs, which is sort of what you'd expect, right? So to build wide fan-in gates with inverting logic, you tend to get these layers of NAND, NOR, NAND, NOR, NOR, NAND, NOR, NAND, something like that. We can do everything we need to with inverting logic. We just have to screw our thinking cap on a little tighter. Okay, so your library is full of these. These are the good gates to use. If you can ever get away with using inverting logic, for instance, in Lab 1, you have to build a logic equation. It's very tempting to build it with sum of products, and that'll work fine. But if you need it faster, then you can build it out of inverting logic, right? And so here's how you do a wide fan-in NAND. So this is an 8-input NAND gate. Notice it doesn't have a NAND gate in the middle. It has a NOR gate. Same thing with OR, 8-input NOR. It has a NAND gate in the middle. And here I just sort of show the demorganized version. Okay, so the key point here is remember this slide and come back and use this. To design the computer, we're going to need a 32-input NOR gate. And the first thing you'll do is build a giant tree of 2-input NORs and wonder why you're getting the wrong answer. So then you'll suddenly remember, wait, Chris mentioned this in lecture 4. Come back to slide 10, and you'll go, I know how to build a 32-input NOR gate. It's going to be a layer of NORs and a layer of NAND and then a layer of NORs. Or maybe you won't remember that. Maybe your friends will. Okay, so sum of products. So here's a sum of products written as NAND NAND. So this circuit here is exactly a sum of products of this equation we've been working with. Okay, it has this logic equation we're trying to implement, but instead of AND and OR, I've drawn NAND and NAND. So first, we should convince ourselves that this is actually a sum of products implementation. What I'm going to do is to replace this 3-input, this NAND gate. I'm going to use the demorganized thing. I'm going to use an OR body with inverting input. So I'm going to turn my AND with a NOT on the output into an OR with NOTs on the input. So that's the De Morgan equivalence. And if I do that here, I've really just redrawn this guy with an OR body on the output and then moved the bubbles on the inputs here. And now all these bubbles match up. And now you can sort of see that it truly is a sum of products. It's implementing this equation here. It truly is a sum of products. Okay, even though I drew it as NAND NAND. After a while, so whenever I start drawing sum of products, I don't think about it too hard. I think this in my mind, and I draw this in the schematic. I just use NAND gates everywhere, and I'm good to go. I can do the same thing with NORs, okay? But you can see I need a lot more inverters to make that work out. And I can go through the same sort of bubble game where I'm demorganize all my gates and then get rid of all the extra bubbles. Given this looks short and sweet, right? This doesn't use any more logic. This just uses NAND gates instead of ANDs and ORs. This one seems to involve a lot more inversions. Is there ever a time when those more inversions are a good idea? Yeah.
When your truth table has a lot of inversions in it, and when you invert, then maybe you use NOR.
Right. If I had a logic equation that had a lot of knots in it, NOR then I wouldn't have to draw all the. I could use the NOR gate to sort of get rid of those inverters. The other thing I want to mention is Think about A. So this guy has A connects to an N-FET and a P-FET in this gate as part of the logic of that NAND, and an N-FET and a P-FET in that gate. So it's actually connecting to the gates of 4 MOSFETs. How many MOSFETs does A connect to in this schematic? 2. Right, so it's actually connecting to half as many gates of MOSFETs. Most of the capacitance, or a lot of the capacitance comes from the gate capacitance of those, the gate of the MOSFET has a lot of capacitance associated with it. So that means that I've reduced the capacitive load on A by a factor of 2 by drawing this schematic. If A goes to a lot of places, that may be a significant difference. If I can take the capacitive load and make it half, the A signal will probably be, the transition on A will probably be twice as fast. So this sort of hack here of putting in some inverters, which seem to serve no useful purpose except sort of get in the way, they are a way of reducing the load on particular outputs, or perhaps being able to building an inverter with a very wide P-FET and a very wide N-FET, be able to drive a very heavily loaded signal. So this guy, the pull-up path involves 3 P-FETs in series. This guy, the pull-up path involves only a single P-FET. So we can actually build a much higher performance circuit in terms of how quickly we're able to make Y change using this circuit than we could with that circuit. So this is small and slow. This might be much larger, but also much faster. Let's think about logic simplification. What I want to do is to look at my big equation, and I wonder, is there an equivalent little equation? And so here's lots of rules for Boolean algebra. You sort of look at these and you go, oh my God, that's a lot of rules. And you say, well, you can fool around all afternoon. Which one should I apply? There's often many that you could use. Which one is going to get me a smaller equation? I want to start with a big equation, do some simplification, and end up with a smaller equation. The key to logic simplification is this operation here called reduction. Okay, and if you look at this logic equation, you can say, look, this is telling me this is true when A is true and B is true. It's also true when not A is true and B is true. These are the two situations. And in fact, it sort of is what this equation, this on the left-hand side is telling me is when B is true, it doesn't matter what the value of A is. It can either be true or false. The answer will still be true. So if I wrote this, I can just as equivalently write B. So I've taken a logic equation here that involves 2 ands and an or and an inversion, and I've turned it into an equivalent logic equation that doesn't use any gates at all. I just borrowed one of the inputs. So if I can find places in my logic equations to apply this particular Boolean transformation, this logic simplification, I can make big logic equations into smaller logic equations. Okay, I wrote this right on the first slide. This is the equation we've been working with. And I'm going to use this reduction identity here. I'm going to, in fact, instead of writing it using only single variables, I'm going to let alpha be any complicated expression. So I'm looking for something that's expression in A, an expression in not A, and then I can just turn that into expression. So let's apply that to this equation. Can I find any instances of this pattern where I can apply? And indeed there are. There's 2 right here. I have C and B and not A, and C and B and A. So I can convert this 2 product terms into a single product term involving just C and B. Good? Right? And I can actually find one more such pattern, okay, here involving not C and A. So it's B that doesn't matter in that case. So what I've done is using this simplification rule, I've gone from a product term that involves 3 input AND gates and a 4 input OR gate into something down here that involves 2 input AND gates and 1 2 input OR. The logic you have to implement down here is much smaller than the logic circuit up here. It's smaller and faster. There's no way in which this isn't better than that. Now you're probably saying to yourself, a lot of work. Now, I'm a computer scientist, a 6'3" guy. That's how I started out in life. And then, people started showing me these things I had to do to design logic, and I started, it's easy to start to say, wait, I don't do hard work. My job as a computer scientist is to write programs to do hard work. That's what I do. And so people started saying, let's write programs that will actually look for opportunities to do this sort of simplification. So I could type in this, or in fact I could just type in the truth table, and I would expect to run a program that would generate this very small, compact logic thing. And in fact, modern computer-aided design programs do exactly that, logic minimization, Boolean minimization. It turns out that it's very hard to, the complexity of producing the optimal equation grows doubly exponentially with the number of inputs. Right? So 2 to the 2 to the n. So if I go from n equals 8 to n equals 16 inputs, it suddenly turns out that the amount of work the computer has to do to find the minimal logic implementation is astronomically larger. So what do we tend to do in situations where the actual problem is super hard? How do we get around that? We use heuristics. We say, look, I can't possibly exhaustively get to the absolutely optimal answer, so I'll use some heuristics to make guesses about strategies that will work. So modern logic minimization programs aren't guaranteed, particularly in large logic equations, to produce absolutely the minimal thing, but they do a very good job. So automation really does do a good job. What we're looking for, what the reduction operator is doing, is it's looking for variables, it's looking for situations, combinations of inputs in which when a particular variable doesn't matter, so we can eliminate it. So for example, if I look at these first two rows of the truth table, or if I look at this row of the truth table and that row of the truth table, this row and this row, when A is 0 and B is 0, when A is 0 and C is 0, in both cases I get out 0 independent of the value of B. In other words, that's a situation when A is 0 and C is 0, the value of B doesn't matter. I can ignore B when A is 0 and B. So what I've done is capture that information in this row by writing when C is 0 and A is 0 and B is don't care. So I either write typically a dash or an X depending on my mood. And so this is a sort of a compact truth table that uses don't cares to indicate when a value doesn't matter. And now you can see I actually have gone from 1, 2, 3, 4 product terms down to 3 product terms by identifying all the don't cares. Okay, so what we're doing is we're sort of looking for these sort of, trying to figure out how to systematically construct this sort of truth table from the full truth table we started with, because that will help us identify places we can use get smaller logic expressions. So you can say, well, I probably would always prefer to use this set of 3 terms instead of the 4 terms I started with. The terms are smaller and there's fewer of them. And so in fact I can use just these 2 terms alone to completely, and this is the simplification we came up with earlier, to completely implement y. So I can draw this logic schematic for y. When I run this, what I discover is that there are some situations, for instance, when both A and B are high and C goes from high to low, the value of y doesn't change. In other words, when both A and B are high, the value of C doesn't matter in this case. But because of the way this particular implementation works, this particular sum of products, when C goes from high to low, we're going from the bottom product term being on to the top product term being on. And there's actually a small delay between when this one turns off and when this one turns on. It produces a 1 on its output, induced by that inverter. Okay? So the fact that there are different length outputs, different length paths from C to the output is potentially producing this little glitch. Now you can say, well, the propagation of the delay of the gate is out here somewhere. The propagation delay of the gate is out here somewhere. So you're not allowed to be looking at the output. You're looking at it too soon. But there's reasons why I might want to get rid of that glitch, even though in theory, logically it doesn't matter because I'm only going to use the output after the propagation delay. I'm going to leave enough time for my circuit to operate that the glitch will have disappeared. But why might I get rid of the glitch? Why would I think getting rid of the glitch is a good idea? So every time I make a transition, I'm charging and discharging a node here. So I'm discharging that node and charging it up. That adds noise to all the current flowing adds noise to the circuit. The other thing it does is it dissipates power. right? So anytime I can design a circuit so that if it doesn't have to change the output, so Y was 1 before C changed, and if I wait long enough, Y will be 1 again after C has changed. If I can eliminate this power-wasting, noise-inducing glitch, that's probably good in modern circuits where I'm trying to run all day on a small battery. So in fact, by including all the product terms that we identified on the previous slide, all 3 of them, in the implementation, like so, I can actually produce a glitch-free implementation. So if there's a way to design a circuit that doesn't have a glitch, this is a systematic way of doing it, including all the so-called prime implicants. Okay, so we've designed a gate that when A and B are high, C can change all at once and the output will be unaffected. That's called a lenient implementation. There's a systematic way of designing such circuits, which we'll talk about in recitation. So I'm going to skip over this is basically a graphical technique for finding variables that don't matter in certain situations. Okay, so I'm going to skip over all that, and we're going to go down here and pick up the slides here. We'll go over Carnot maps in recitation. But you have a bunch of slides that describe to you exactly the process. So the truth table that I've been describing is called a multiplexer. It's the actual circuit that we're going to use a lot of. Multiplexers will be our friend, particularly when we get to the beta. So here's a multiplexer. This is the schematic symbol, and the schematic symbol is designed to tell us what's happening. We have 2 data inputs, and we have a control or a select input. When the select input is high, we're going to take the value on the D1 wire and make it the output. And when the select signal is low, we're going to take the value on the D0 wire and make it the output. In other words, the so-called multiplexer is taking 2 incoming values, a 2-to-1 multiplexer takes 2 incoming values, chooses one of them, and makes it the output. Allows us to choose which one of the 2 inputs to use. 2-to-1 multiplexer, which we usually just say mux. It's a mux. Okay, I can actually build 4-to-1 multiplexers and 8-to-1 multiplexers and 16-to-1 multiplexers. I can actually build them all out of little trees of 2-to-1 multiplexers. The number of inputs is always a power of 2, and it's like 2 to the k for some k, and then the number of select lines is k. So a 3-to-1 multiplexer, an 8-to-1 multiplexer has 8 inputs, 2 to the third inputs. Okay, and it has 3 select lines, some combination of which will select which one of the 8 inputs will become the output. So that's a multiplexer. Why do we like multiplexers? There's many reasons, but today's reason is that we like multiplexers because they let us do a systematic implementation of logic. I can design any logic, implement any logic function very quickly with using a multiplexer. Here's a 3-input logic function. I've just written down a bunch of things. This turns out to be the carry-out logic for an adder circuit. Here's the truth table for it. If I use an 8-to-1 multiplexer, and notice I've hooked the 3 inputs, the A, B, and C in inputs are being used as a select line here. So depending on which combination I have for the inputs, if A is 1, B is 0, C is 1. So I have 8 possible combinations here, and I'll select one of these 8 input wires as the output. So that's what the 8-input multiplexer does. What I'm going to do is simply wire up constant power and ground, 0s and 1s, to the inputs to the multiplexer, and these 0s and 1s are exactly the output column of the truth table. I didn't have to think about logic minimization or sum of products or building a customized circuit. This is a general purpose circuit for implementing any 3-input Boolean equation. You change the output, you give me a different equation, change the output here, I'll just change some constants that I would wire to the inputs here, and voila, I have a brand new circuit that still computes the new function. I didn't have to change anything except a few constant connections. So again, we get to the sort of 6-3 end of the world. You know, logic minimization is fun and neat, but that's sort of an EE thing. CS people said, look, can I just write down one general purpose answer and just use it again and again and again? And the answer is yes, multiplexers are a systematic way of implementing any logic function, particularly when they have a small number of inputs. And in fact, we can buy lots of programmable logic. I'll show you some right at the end of the term. Little chip that basically you can program it to compute to perform logic for you. Not in the sense of writing a program that computes ands and ors. I mean that what I'm going to do is configure multiplexers to compute logic functions for me, and I have 1 million multiplexers on the chip, so it's equivalent to a million logic gates that I can determine how the logic gates work. It's a neat technology. Okay, so I can certainly use, here's a 2-input logic equation. I can use a mux to implement anything. For an n-input function, I need a 2 to the n input mux. So once I get to 5 or 6 or 7 inputs, muxes are starting to be impractical. But for up to about 6 inputs, muxes are very practical. And in fact, field programmable gate arrays tend to be built from these little 6-input programmable logic functions. Okay, muxes are, as it turns out, universal. I'll show you how to use a mux and some constants and the input values to compute any logic function I want. It could be that modern molecular scale technologies and switching logic may not be the universal thing. It may be the selection logic. It may be that the chemistry of life or carbon nanotubes or things like that. It may be that the circuit configurations we come up to, we're able, the circuit element we're likely to be able to build may be a multiplexer rather than a switching circuit. Maybe a multiplexer. So the good news on this slide is 10 years from now when somebody says, I can sell you, a giant bucket full of 100 trillion muxes, okay, for not much money, and they run very quickly, you can say, that's okay, I can design any circuit I want. I can design using only muxes. So they may be universal. This is, by the way, an XOR gate as a mux. So muxes, everything costs the same in a mux. One mux can compute any of these logic equations that you see here. Whereas I told you before that in MOSFETs, this is very expensive, but this is very cheap. In muxes, it's all the same cost. Okay, so one final systematic way of implementing logic. Okay, and the building block we need for this final systematic way is called a decoder. It's the opposite of a mux. So this is a so-called demultiplexer or decoder. I take in some number of signals, k signals, and I have 2 to the k outputs. So if k was 2, I'd have 4 outputs here. And depending on the input value here, I select one of these output wires to be a 1. Right? So I'm decoding this, I put in a particular combination 1, 0 on here, and then a single one of these wires would be a 1, and all the rest would be 0. So I'll decode this into one of 2 to the k wires, which will be a 1. You say, well, what do I use that for? And the answer is I'm going to use it to be the building block for a memory system. And the idea behind the memory system is what I'm going to do is I'm going to decode the decoder here. In this case, I have 3 inputs, and I hook them to my 3 to 8 decoder, so I have 3 possible inputs. For any particular combination of A, B, and C, one of these decoder outputs will be 1. In fact, I've shown you the input combination here. So for example, if I put 0, 0, 1 on the input here, this is the wire coming out that will be a 1. What I've done is, in some ways, think of this as a bunch of rows. I've selected a particular row. And then I'm going to build a little logic circuit that lets me read out information on any number of columns that I want. So the idea of this gray box here is actually implementing a little table lookup of exactly this set of 1s and 0s. Okay, and if you follow along with what's happening when this is a 1, this little pull-down transistor gets turned on because it has a 1 on its gate. There's no connection here. So that means that this wire here will be pulled down to 0, and this final inverter will cause it to be a 1. So what I'm doing here is using little transistors to basically program in the information about where the 1s and 0s are in my table. Okay, so this is really a circuit implementation of a little table lookup. It's called a read-only memory. It's a memory system where I can sort of select which row of the table I want to read out, and then by programming in these transistors in the right place, I can cause the table to read out a 1 or a 0 as appropriate. So deep breath, pop up about 12 levels, and you say to yourself, think of this as a systematic way of just taking the output column, the output columns in this case, and simply programming them into a memory system. I then use the inputs to select which row of the table I should read out, I read the information that's stored in my memory. I read that out in that particular memory location. So I'm reading out this particular memory location, and I'm getting out the answer 0 and 1. 0 for S, 1 for C. Yes?
So this information is hard-coded, or
This information in this particular circuit diagram is hard-coded. You own a lot of flash memories in your computer in which we're able to change the information that's stored in any of these locations. So we can, after the fact, program in the information we want to read out. It's a special process, so the memory, you can write it, but it takes a long time and it's cumbersome. You use special power supplies and things like that. So flash memories are designed to be mostly read and very occasionally write. But that's, for instance, how the BIOS in your computer is stored. It's stored in this read-only memory system where you give it an address and it's going to produce a particular value. And so that's how we store the boot program for the computer. Yes?
so the information is stored in the location of each MOSFET, is that right?
Right, so in this particular case, every time there's a little pull-down resistor, I'm going to get a 1 whenever I read out that particular row of information. And if there's no pull-down transistors, I'll get out a 0.
So like all the information you have is just mapped to location of MOSFET that you put on that circuit.
Right, we're just coming up with an electrical way for permanently encoding a set of 1s and 0s. Okay, systematic logic, first of all, how to do any sort of combinational circuit using our gate level building blocks, and then systematic ways using muxes and memories. So with that, we'll stop. No lecture on Tuesday. It's a Monday. Monday's a holiday. Tuesday is a Monday schedule. So calendar Tuesday is a virtual Monday. So I won't see you until Thursday.